Alright, hi everyone, CE495. This is Lateral model tutorial. I tried to create it so you guys actually follow along on next Tuesday. So this is, I think, the typical floor model. I'm gonna just run this model. You guys always start before you move on to the next step. Just make sure your model is correctly completed. So this one, I'm gonna just spot check the moment diagram due to the gravity dead load, which is one single curvature load, or the beam encoder we currently use. Assume this is all the gravity framing. So check the axial force diagram and axial force diagram. So axial force, typically you want to see or how much loads take go to each adjacent the column. You see that the column axial force representing column reactions based upon dead load, which is self-weight, and is based upon their tributary, their own column's tributary area. You see the actual forces varies. So this model seems ready. So I'm gonna unlock. The first thing what we need to do is we need to go to edit and define the floors. Stories information, right? Since this model is one single story, we try to, like here, 15 feet, try to copy 39 times, right? So I think the ETABS has a very simple, quick tool, so we can add stories by clicking this, right, button. Let's see. Assume that each typical floor height is same as 15. I'm gonna click 39 times. Let's see, go up to 40 story, right? And then open the modify and try to look at the story data. So basically, ETABS is copy the floor information based upon existing 15 feet. So this model, just story data, I think we just quickly completed the top of story 40s. We have elevation 600. So I'm gonna just click go out. So you see that all grid is also copied and established based upon each floor 15 feet. All right, so this is quite easy. So next step is we're gonna just double check again. Then by clicking the slab and see what your current design load, right? So STL was, I think this model has a relatively heavy STL, but Lateral 100 and also construction dead load 20 loads was assigned. I want to just make sure checking what do we have in the loads. Yes, we have a self-weight here too. I'm gonna delete just in case wind loads so that I'm gonna show you how to set it up wind loads. So this model is ready for the copy. So I'm gonna select all this column and slab and walls, everything, and go to edit, replicate, go to story tab. By holding down the shift key, you can select all the floor at the same time and then apply copy. Okay. So you just copy geometry and with all the load information. But somehow, since we select all, somehow it applied the boundary condition. You see that all the pin symbol. So we try to select and go to assign and joint, restraint, go to assign, join, restraint, and make a free. There's no boundary condition. Its only boundary condition should be at the bottom, right? So geometric copy is so easy. Since we are building the 40-story building, I'm gonna save as the front file entire, right? Which I already had it. But anyway, I copy. So geometry is copies. The second one's what we're gonna do, we're gonna assign the diaphragm. So what is diaphragm is all the nodes, joints, right? Nodes at each same elevation. We try to assign so that nodes we assume that move rigid body motion. So that is actually saving some computation time a lot, and also based upon rigid diaphragm, that wind ETABS can calculate the wind load and for user. So I think that's easy. First things, there are too many the way to do this. I'm gonna put the 3D in XZ plane 3D. Well, how are we gonna do it? I'm gonna select all the nodes above the base elevation, right? Or maybe select all, and basically I select all, but assign border joint and diaphragm here, right? And so D1 is default. Let's see what is D1. So define diaphragm, diaphragm D1. When I click modify, there is two type of diaphragm. One is rigid, the other one is semi-rigid. We're gonna keep the rigid, so we're gonna assign rigid diaphragm. You see that all the dash line is assigned every floor, right? So let's go check the plan. Okay, so all the node joint on is the same elevation is really tied with this rigid diaphragm. So if you walk down this buttons, right? This looks like same. But one thing you might be check it, because since I select all the nodes, it assigned to the base. Also rigid diaphragm, but we have a boundary condition there, pin. We don't want to duplicate the rigid diaphragm. So I'm gonna go to joint and diaphragm. I'm gonna disconnect this, right? So let me see. So here you see that all the dash line. I'm gonna just rotate. All see every floor above the base level. We have all the rigid diaphragm. All right. So there is a rigid diaphragm. Now let's define, and we're gonna define the wind load. Before we go to wind load, let's take a look at our New York City Building Code. So I just opened the New York City Building Code current in chapter 16. You see that table show us the basic design wind speed here mile per hour based upon 3-second gust at the reference elevation 33 feet, exposure C. So this is a reference our basic wind speed, but it varies along the risk categories. Obviously, this category 1 has the lowest wind speed, which means it's lightly treated, like an agricultural building. But 3 and 4 has a more heavy, higher basic wind speed, means this more essential building, so we try to treat a little more highly, right? But like the commercial building and general office and residential building, we treat as a category 2 typically, so we're going to use 117. But you have to always remember that now all the winds and seismic load is ultimate load, which means you don't have a load factor. Load factor should be 1.0, right? So this is the ultimate basic wind speed. I encourage you to just remember that what is relevant, the return recurrence interval years for this category 2, which is 700 years. Once in a 700 years returned wind, the wind speed is 117. But as for serviceability building, we did the homework 1, we checking building deflection, right? So the 117 here is ultimate wind load. So we are using this wind speed for wind load calculation, which ultimate wind load calculation for our strength design. But the building, because of the tall and building also the foam display and moves based upon the wind load. But at the cases we same as live load, and on another total dead load plus live load, we're using service wind load without load factor. So, which I think typically our practice building deflection check for high-rise building, we used to use a 50-year wind interval wind, so we could calculate the wind load based upon reference wind speed 93 miles per hour, which is give us the reference serviceability wind load. So we're gonna first of all we're gonna define the wind speed to calculate the ultimate wind load, right? So go back to our ETABS and define a load pattern. We're gonna create the wind X and change to type wind load. Since we are following ASC 7-16, it should click it, and I'm gonna add it. Oh, wait a minute. Win X, win 7 ASC 7-16. So I add it. So I'm gonna modify the wind load factor, which 117. And typically Manhattan inland is exposure C, offshore exposure D, right? So we're gonna keep it since we are just setting the wind loads. But I think at this point we're gonna focus on the wind is just blowing in global X and global Y. But obviously we need to consider all winds blowing in all 360 degrees, which is creating total load cases 12. But for current study, we're gonna just choose one so that we try to create the wind is blowing in X direction and Y direction. So wind direction here we need to define since we have diaphragm assigned. I think it's already ETABS calculate the total building width and depth, right, based upon their footprint. And also angle, direction angle, we need to create the wind is blowing in global X direction, which is, I think this direction angle should be 0, means wind is blowing in parallel to the global X coordinate direction. All right, so we create the wind load in blowing in X direction. Well, why don't we create another wind so that we can create the wind blowing in Y direction, right? So I just open it, but I'm gonna fill in same information here. Just we're gonna consider load case 1. When you click it, you see that wind direction also the building width and depth is already calculated, but at this time wind is blowing Y direction, so this angle should be 90. So I just create the wind X and wind Y for our first initial analysis. So I think it's ready to run, right? So basically, we haven't designed anything, right? Just copy the geometry, which is based upon typical floor at the bottom. We're gonna analyze it. Let's see. All right, I think default ETABS always show the displacements under the download. So you see the exaggerated deflection, which relatively small. But we're gonna just check again, since we just copied 39 times, you might be interested how much load, what would be the column action forces, right? So you just turn on and just always curious about what's going to happen. An engineer should always curious about our input and associate expecting output. So all the red color means compression forces. Obviously, this is just summation, cumulative actual force, because we have dead load here. right? Each column takes some their reaction, but you basically you have a 40s floor, so they just sum them up, right? So it should be gradual, as it like as shown like this. So what we're gonna check is first we're gonna go on configure this interesting button. Okay, I'm gonna put on the plan 40s floor. I like to show the deformation shape. Deformation shape and choose the wind extraction and click it. You could animate it and see whether your wind is assigned is correctly. Because of wind X means wind is blowing in global X direction. Common sense, the building X should move in X direction, right? Wind Y, I have to stop and I change to Y and I create the Y. So wind Y, we assign the wind, define the wind loads, all the parameters, but angle we type the 90 degrees. So I think that is correctly assigned. I'm gonna put it in 3D. If you're interested, you just animate it on 3-dimensional model. So you could see that this is wind Y, right? This is red is X, green is Y. So you could just play around first. This is something that at the beginning that how we kind of verify our input and associate output. Some geometrically everything is connected. Looks like column load takedown actual force diagram looks right. Deformation shape, the wind X actually blowing X, so the building move in X direction. Wind blowing Y makes the building move in Y direction. So we're just checking gravity graphically. Visually, we can see it much clearly. All right, now there are many ways to we can also check and grab all the output from the display. The menu, we could also check the what will be our deformation shape by clicking story plot. So here default is showing dead load, but we are interested in X direction. So you see global X. So blue wind is blowing in X direction. So deformations, displacement should be in X direction, right? We just show the maximum story displacement. So you see that 7 inches. But if you change to Y, obviously this displacement is happening in global Y. You see the maximum, wow, so 40 something inches, right? Because now it's time to look at your lateral stiffness. Obviously we copy all the elements all the way up, but by looking at this building geometry and our structural wall, you always try to, you can just figure out what this guy building actually perform under the wind load. Wind is blowing X direction has a tributary width about 40, 30, 40, which is 110 feet. But wind is blowing Y directions, I think wind speed, wind pressure is the same, but the building is 150 feet wide, right? So you could see this overall total wind blowing in Y direction is bigger than wind blowing X. That causing obviously the total base shear due to the wind Y is bigger than X because the tributary width, right? Surface area is bigger in Y direction, which you can guess it, 150 divided by 110 is something more like the ratio between the total wind load in Y direction, which is base shear, and is greater than X, by the magnitude of order of 150 divided by 110. But the wind is most likely wind load is based upon building geometry, but you could see that your core layout, right, and their associated stiffness is kind of the other way around. The building, our core is layout in most likely X directions. That this concrete core wall overall stiffness is much steeper in X direction than Y direction. I think you study homework 1, but then now we're gonna make 3D. So you know that what is the reference as stiffness, which one is strong axis and the other the weak axis by looking at the core layout. So that explains us that wind is blowing Y directions, only just a little bit 150 divided by 110, which is what ratio 40% more. Yes, 36% more, but deflection, what we end up mostly 40 inches divided by 7 inches, right? Almost, right, 6 times bigger. So we need to really now move on, understand the overall stiffness, how we can get the enough stiffness by playing with the concrete strength and by playing with the increasing wall thickness. If not enough, then we need to incorporate some outrigger trusses or other trusses lateral elements. So why don't you practice? I think we're gonna practice. We're gonna have a workshop next Tuesday, and you're gonna just watch it and follow along. I hope this is helpful. And once we get there, we're gonna just discuss about how to play around, define the wall, various wall thickness, and also concrete strengths, which means Young modulus, and also how to assign the elements along this height, because we're not going to use the same size all the way up, because obviously that is wasting our material. Basically, we're going to make the member bigger at the base and lighter at the top, right? As similar to column design, we try to size the members based upon their demand. All right. All right. So this is the end of the video. I think I'm gonna send all this video. Hopefully you guys watch it on Monday or Tuesday, or because we need to move on faster. Hopefully within next 1 or 3 weeks, we try to get this done. But this is more fun than you guys can play around. This is really nice 3D animations and simulations. Things really kind of cool to play around. All right. Then see you Tuesday. All right. Bye.